All right, Zoomies, can you hear me? Perfect. We fixed. All righty. So let's go ahead and get started. Today's in-person class is brought to you by the name Julie. It's the only people who are here in person. All right, so today we are talking about repeated measures, Anova, or analysis of variance, right? So last time we talked about sorry, you got beaten out to it by two others. Y'all are getting good here. So last time we talked about essentially a one-way Anova, right? And so this time we're going to be talking about what happens when you have the same participants in every level of the independent variable. So before we do, what did we learn last time? What do we know about ANOVAs? Yeah, so we use an ANOVA when we've got 3 or more groups. Exactly. What are some of the key differences between an ANOVA and a t-test?
You're measuring between and within values.
Yeah, so we're measuring between and within, right? And so, yeah, so Amanda says using mean squares, right? And mean squares is just essentially a fancy term for what?
Variance.
Yeah, for the variance, exactly. So we're using mean squares. The F ratio is just a ratio between the variance between, or at least in a one-way ANOVA, between, over, within. Yeah, good job, Amber. So yeah, we are going to be moving on from that, and a lot of the principles are going to stay the same. However, we're going to add a new component in, because when every participant gets every level of the independent variable, they serve as their own control, right? And so as when we used the repeated measures t-test, we got that difference score, that D score, that was benefiting us because every participant served as their own control, and we didn't have to worry about the variance in between participants because we were excluding that, right? You can't get that difference score when you've got 3 groups or 3 or more groups. And so what we're going to do is a little bit different, but it's the same idea, right? We're removing any of that variation inherent within the individual participants. Questions about what we learned last time? All right. So here is your fun fact of the day. According to scientists at Purdue University, it officially takes 364 licks to get to the center of a Tootsie Pop. There you go. One for every day? Exactly. But look at that. You get more than one Tootsie Pop every day, or every year, rather. Or every day, depending on, yeah, how diabetic you want to get. All right. So let's first start talking about just kind of the logical background behind why we're even doing repeated measures ANOVA. Right? And so last time when we did the ANOVA, Jay says, what's the confidence interval on that fun fact? That's a very good question. Yes, how consistent are those Tootsie Pops? So before, or I guess on Monday, we talked about the repeated measures, or the ANOVA rather. You're doing a test between 3 or more different conditions. But as with anything where you have different participants in every group, you're going to have some degree of sampling error that's dictating those differences between the groups, right? So the best example of this is go to a website like Real Clear Politics that has all the presidential polling averages, and you see how much they bounce around from poll to poll, right? In theory, they're measuring the same population, but pulling from that population, you're just going to get a lot of bouncing around between that. And so one alternative to dealing with that type of error, or that type of variance, is to do what we call the repeated measures test, right? We do the repeated measures for the t-test, we do the repeated measures for the ANOVA. And that's going to allow us to remove any of those individual differences between those different groups. Right? So again, conceptually, let's just go back to presidential polling because everything has to be politics now. If you take one group, get a poll number, and then take another group and get another poll number a week later, you don't know if that represents a real trend in the political polling or if you just polled a slightly different group that gave a slightly different average. Now, if I poll 100 people today and then poll those same 100 people in a week, I can be pretty sure that any difference there is not just due to individual differences, but actual changes in opinions. Right? And so that's the whole idea behind what we're going to be doing with this repeated measures test, right? So we're going to be doing a second stage, which is going to try to remove those individual differences, which is going to allow us to, with better certainty, say that a difference between groups is likely due to the treatment effect and not just individual differences. So the repeated measures design eliminates those individual differences from the between treatments variability. Like I said, because we're using the same subjects each time. To balance the F ratio, the calculations require that the individual differences also be eliminated from that denominator. And so we'll go over how to do that as well. But if we're removing those individual differences from the numerator, that mean squares between treatments, we need to remove those individual differences from the denominator of that mean squares within treatments, right? And so we're going to have slightly different terms that we're going to be using this time. So that independent measures analysis is used again when we've got three different groups, comparing that variance between the treatments to that variance within the treatments, creating this ratio that we used last time. But again, what makes this different is that we have to remove that variance inherent to those individual differences. Right? So whereas for the traditional one we were using had the treatment effect plus the error, which was going to include those individual differences, divided by the error, which included those individual differences, we're going to be getting rid of those individual differences with this repeated measures. And so this is going to be essentially just that remaining error. I once had a student who saw me drinking from a variety of cans, and I guess didn't have very good eyesight, thought it was a beer. I feel obligated to tell y'all that I'm not drinking beer at the front of class. Yeah, I want to keep my job. I'm not doing that. All right. So again, just regurgitating this. So in the repeated measure study, there are no individual differences because we've removed them by testing every participant in every level of the treatment. This means that we don't have any individual variance in that numerator. Right? There's no variance between the groups as a function of individual differences because all those individual differences have been removed. Therefore, we have to remove those individual differences from the denominator to maintain that balanced ratio. Right? Because if we remove one source of variance in the numerator and don't remove it from the denominator, we're not going to have an artificially deflated F ratio because we're accounting for variance that we don't need to account for in that denominator. So what does that look like? We are looking at the treatment effect, per usual, in that numerator, plus any residual error that is not a function of those individual differences divided by that remaining error with those individual differences removed. So again, it's still conceptually the same thing. We have the same error notation, numerator and denominator, with that treatment notation up there as well, such that now we can see how many times bigger is that treatment effect than the other variance. Questions about any of this so far? Is this all making conceptual sense? Cool. Cool. All right, so whereas we had that kind of single stage, and you'll see the differentiation between the single stage and today what's going to be this sort of two-stage analysis. In the first stage, we get that total variability, just like we did before. And that total variability, that sum of squares total, or that mean squares total, is partitioned between the between treatments sum of squares and the within treatments sum of squares. So this first step is just what we did last time. So the components for that between treatments variability are the treatment effect, if there is any treatment effect, and error. And because those individual differences don't appear, because we're using the same subjects, on the other hand, individual differences do play a role in that sum of squares within, because the sample contains different subjects, right? It's not the same person you collect 10 data points on for each condition. It's 10 different people you measure. So I don't have much room to draw here. Actually, let's go back to the first slide and just draw this. All right. So what that's conceptually saying is we have condition 1, condition 2, move that, condition 3, and we have subject 1, 2, 3, 4, etc. 1, 2, 3, 4. And 1, 2, 3, 4. All right. So what this is saying is the variance between these groups that we had to account for with the one-way ANOVA or independent measures ANOVA is removed because it's the same participants from condition 1 to condition 2 to condition 3. Yes, yeah, exactly. However, we still have a source of individual differences affecting within each condition, right? Because this person is different than this person, which is different than this person, etc. Right? And so whereas we've removed the variability between these groups, we haven't yet removed the variability within these groups, right? And removing it within these groups is what we're going to be doing today to allow us the benefit of a repeated measures ANOVA. All right, so in this second stage of the analysis, we measure the individual differences by computing the variability between subjects. Sure, record this again. All right. For those of you all who are watching the recording, it's going to be a little disjointed because we just lost Wi-Fi, and I'm starting again. And so now I'll share the secrets of the universe once more, only because I care about y'all. All right. So I don't know exactly where it cut out the last time, but we will just regurgitate the slide really quickly. So in the second stage of the analysis, we measure those individual differences by computing the variability between subjects and removing that from the within to give us our sum of squares error. Right? And so now we have several different things, right? Besides my entire technology stupid. I'm going off the grid. See y'all never. All right. So we have our sum of squares total, right? We have our sum of squares. What the hell just happened? Sum of squares within. I'm telling you, man, the technology is out to get me. We have the sum of squares between treatments, the sum of squares between subjects, and that sum of squares error. So again, just to represent this, we have our total variance, which can be separated into the between treatments variance and the within treatments variance. All right, the between treatments variance is a function of that treatment effect, but also a component of error or chance, right? Just anything associated with sampling, we're going to get a little bit of noise in there. And then we have that within treatments variance, which is a function of individual differences, and then whatever other noise was inherent in that between treatments variance still exists here. Right? And so for what we did on Monday, stage one is all we needed, right? It was degrees of freedom between divided by degrees of freedom within. But now we have a brand new stage where we have to separate this within treatments variance into the between subjects variance, so those individual differences. Once we get those pups, we remove them from that within treatments variance, and the remainder is that error variance. So that error variance, excuse me, now becomes the denominator for our F ratio test. So again, you can see how this, everything above this was from Monday's class. Now, we're just taking this and adding one more step. We got to get rid of this bogus individual difference variance. Once we do, we're ready to rock and roll. Questions about any of that? Awesome. And so to get those mean squares, it's a very similar, it's actually identical to what we did on Monday, right? Or what we've been doing all semester of getting that variance, which is just the sum of squares of interest divided by the degrees of freedom of interest, right? So to get the mean squares between treatments, we take the sum of squares between treatments and divide it by the degrees of freedom between treatments. To get the mean squares error, we take the sum of squares error and divide it by the degrees of freedom error. And now our F ratio is that mean squares between treatments divided by that mean squares error. Got the world's itchiest nose today, which is not good during COVID. All right. So one of the biggest points of confusion I see on the exams is people getting tripped up with the between, right? We have two betweens now. We have between treatments and between subjects. The between treatments is what we're interested in for that F ratio. So between treatments is always going to be in that numerator. The between subjects is what's going to help us get that error, but we ignore it for the F ratio. So I know you're probably thinking, all right, what the hell is the point of doing this repeated measures test? Because it's just going to add extra steps. So why don't we just get different groups of participants for everybody else? Well, aside from the fact that it cuts down the number of participants you actually have to recruit, one of the benefits is that when you've got large individual differences in a population, those can obscure minute differences in an actual treatment effect. Right? So if there is a massive amount of variability in what these presidential polls are saying, a small change, by 1 point change in the actual difference in how people feel in the presidential poll may be obscured by the fact that we have these massively variable outcomes for those polls. And so when you're studying something with a small effect size, right, something that isn't necessarily going to have a large Cohen's d or large eta squared, it's a small effect, but it's worth studying. Doing a repeated measures test is going to allow you to more easily parse out that between treatments effect. All right, so here's just an example of what everything's going to be looking like, and we'll walk through this in a little bit more detail moving forward. But just to kind of preview everything. So let's say we have 5 participants who receive a placebo and then 3 experimental drugs. All right, so they have the placebo, they have drug A, drug B, drug C. For each one of these columns, we do what we did before, right? We calculate the mean for those, and we calculate the t. And what is the t again?
The sigma of each x.
Mm-hmm. Yeah, it's just the total for that column, exactly. So we've gotten all that. The total, it's just the total for each column. He said sigma x, so it's just sum all of the x values in one column. It does say 8. That must have been a typo in the book. Yeah, so that should be 5. I don't know. Math is hard, okay? I know. Yeah, and this is from the book. How about that? That's not, for once, it's not my fault. All right. And so we have a couple other things that we know from last time, right? What is K? What does K represent?
How many
It
sets
does
of samples there are?
Yeah, how many different treatments there are, right? And so in this case, we have 4 different treatment effect or treatment conditions. What does big N represent?
The number of total individuals.
Yeah, number of total individuals, or in this case, number of total observations, right? So we only have 5 individuals, but we have 20 observations, 20 individual data points. What does G represent?
The total of all the totals.
Yeah, total of all the totals. Yes, exactly. Yeah, so you're just adding up all the data points, right? It's the sum of all the T's or the sum of all of the individual data points. So. And so now we're adding one new tidbit here. We're adding these p-values, except they're not the p-values we normally think of, right? So this is capital P. And so these are the person totals across the treatments. Right? Yes. So for person A, we add up 3 plus 4 plus 6 plus 7, which does equal 20. I got that one right. For person B, 0 plus 3 plus 3 plus 6 gives you 12, and so on. So now we have the column totals and we have the row totals. Right? The row totals are the totals for the person. The column totals are the totals for the condition. Everybody with me so far?
No.
No, okay. Where did I lose you?
The P's, like, okay, so N is for all of the participants.
Mm-hmm.
If they're, okay, so
If you
I don't
think of
know.
like, if you think it's like the total for each person, like person A, because remember it's like the same, these are the same people being used in each like drug.
Yeah, so, but, okay, so person A is like just one person.
Right. Remember it's
Yes.
repeated measures, so it's the same.
Okay,
It's
so
only-
why would the total of people be 20?
So
For
it's
the
not the
placebo.
total of people. It's the total for, so think of that first P as P subscript A, right? So it's P, it's just the total for person A. So 3 plus 4 plus 6 plus 7 across, right? So I'm taking for person A, I'm taking every one of their scores and adding them together. For person E, right, so we could do P subscript E, I'm doing 0 plus 1 plus 4 plus 3 to give me 8, right? So P is not the number of people. P is for each person, what is your total score?
Okay, so like person A is one person, and then drug A, if you were to put it in, I don't know, like they took 4 pills, or they have on a scale of 1 to 10 4 pain. Like I don't know what.
Yeah.
Just go with that.
Exactly. So whatever that dependent variable of interest is. So let's say person A is you, Amber. And so let's say these are ratings. And so when you took the placebo, you gave a rating of 3. You then took drug A and you gave a rating of 4. You took drug B and you gave a rating of 6, and you took drug C and now you gave a rating of 7. And person B, we'll say, is me. And so I took the placebo and I gave a rating of 0. I felt like crap. Once I took drug A, I gave 3. When I took drug B, I gave a rating of 3. When I took drug C, I'm going to assume that's 6. Does that make sense?
Yeah. So if we're totaling all of that together, why exactly?
Yeah. So that's going to allow us to get that individual differences variance, right?
Okay.
So when we get the sum of squares here, we're getting what is the variation within this group here, right? So that sum of squares within is a function of this sum of squares plus this sum of squares plus this sum of squares plus this sum of squares. We're doing the same thing conceptually, but now instead of these different treatment conditions, now we're going to do it for all the people, right? Because
Okay, I get it.
got it? Yeah.
Yes.
Because this is going to represent a whole new source of variability that we're going to remove. Good questions. What other questions do we have?
Could you go over the G?
Yeah, so G is just going to be the grand total, right? So for G, I'm adding up all of these scores together. So 3 plus 4 plus 6 plus 7 plus 0 plus 3 plus 3 plus 6 plus 2 plus 1, etc. Does that make sense?
Yeah.
Mm-hmm. All right. Go ahead and move on. So the total sum of squares of the equation is the exact same as we used last time. The sum of x squared minus the sum of, minus g squared divided by n. So what am I doing to get this sum of x squared?
You take each, well, I guess you would take each x and then you'd square it just like we've been doing, and then you take the total of all of those x squared values.
Exactly, yes. So for every, I wish I hadn't made such a mess, but let's look down here at the bottom. You're taking every individual x and you're squaring it, and then you're adding all of them together. Good.
Except the p values, right?
Yeah, so those p's, you're just ignoring, right? Those p's are like the t values, right? So we're just taking what our initial data is, ignoring the means, t's, the p's, the g's, any other letter.
Got it.
All right, so we're taking the sum of every x value squared. We're then subtracting from that grand total, that global total, which we've then squared. And we're dividing by the total number of observations. So whereas in that previous example, we only have 5 participants, we have 20 observations, right? So big N is now not the number of participants, it's the number of data points we have. That between treatments sum of squares is the same as what we did on Monday. And it's just a function of that total sum of squares minus the within subjects sum of squares. Or you can do it computationally, such that you're taking the sum of t squared divided by n minus, again, that g squared divided by n, right? And so in this case, we have our t values down here. And so to get that, it would look like 8 squared divided by, what is my n? My n is 5 for each one of those, divided by 5, plus 10 squared divided by 5, plus 20 squared divided by 5, plus 25 squared divided by 5. I'm adding all of those puppies up, and then I'm subtracting that g of 60 60 squared, that's supposed to be a 2, divided by the total number of observations, which is 20. So again, that's nothing new. The within treatment sum of squares, again, is not new. It's just all of those sum of squares for each treatment condition added together. Right? And so we get a sum of squares for placebo. We get a sum of squares for drug A. We get a sum of squares for drug B. And we get a sum of squares for drug C. And our sum of squares within is just adding all of those together to get that sum of squares within. So again, that's nothing new. That's the exact same as what we did on Monday. Now, we're going to add that one new thing to find the between subjects sum of squares. So this is why we calculated that P for each of those rows, for each of those participants. So to get this, it's going to be very similar to the between treatments, but now instead of T, we're using P. Instead of N, we're using K. So that between treatments, again, was taking every column total, squaring it, dividing it by the number in that column. Column 2, total, squared, divided by the number in that column, and so on. The between treatments, or excuse me, between subjects is taking every row total, so in this case 20, squaring it, dividing it by the number of conditions, right? And so this will be 20 squared divided by the number of treatments, which was 4, plus, what do we have for subject 2? Subject 2 had a P of 12, or a total of 12, so 12 squared, again, 4 treatments. Subject 3 is 12 again, plus 12 squared, or 4 treatments, plus subject 4 had 8 squared divided by 4, and subject 5 was also 8 squared divided by 4. So we're adding all of those bad boys up, and from there we are subtracting again that 60 squared divided by n, or in this case 20. What questions do we have about that?
Could you go over the numbers again? Or you got the 20, 12, 8?
Yeah. So those all came from these P, right? These row totals. So for participant A, I add up every one of these values and I get 20. For participant B, I add up every one of these values, I get 12, and so on. And I'm dividing by the number of treatments, which in this case is 4. Does that make sense?
Yeah, thank you.
Mm-hmm. What other questions? All right. Awesome, awesome, awesome. So once we have that between subjects sum of squares with this equation here, to get our sum of squares error, we just take our sum of squares within that we calculated somewhere. Oh, on the same thing. So the sum of squares within, and we're now going to subtract the sum of squares that we just calculated for that between subjects. All right, this is going to be removing any of those individual differences that could be affecting that variance. This couldn't be any easier. Don't worry about any sort of like computational way of doing it. To get your sum of squares error, you just need your sum of squares within and your sum of squares between subjects. Once you have those, you can get your sum of squares error. For your degrees of freedom, the degrees of freedom total is just like we had before. It's just the number of observations minus 1. For your degrees of freedom within treatments, just like before, it's going to be number of observations minus the number of conditions. For your degrees of freedom between treatments, it's just going to be like before, number of treatments minus 1. For your degrees of freedom between subjects, this is going to be new. It's going to be the number of participants you have minus 1. All right, you could also, in theory, write it like that. And then, just as with your sum of squares error, which was your sum of squares within minus the sum of squares between subjects, your degrees of freedom error is going to be your degrees of freedom within minus your degrees of freedom within subjects. All right, so once you have your degrees of freedom within and your degrees of freedom between subjects, you can get your degrees of freedom error. All right, let's do a practice problem here. So let's say I have what I believe is the world's best fitness program. We're going to call it P180X rather than P90X. And I'm going to look at people's well-beings, right? And so before they start working out, I get their well-being score. At 3 months, I get their well-being score. And at 6 months, I get their well-being score. I've got 6 subjects. So just go ahead and ignore the means for the time being. Let's just look at these data. All right, so we have N of 18, right? The number of observations I have for my exercise program test is 18. I've got 6 subjects, and I measure them 3 times. My lowercase n, so the number of subjects I have is 6. My G is 827, So to get that G, that grand total, again, I'm adding up every single data point here. Adding up everyone for the pre and everyone for the 3 months, and then adding up everyone for the 6 months as well. When I add all those together, I get 827. And then to get my sum of x squared, because that'll come in handy later, I'm squaring every one of these values and adding them together. So 45 squared plus 42 squared plus 36 squared plus 39 squared plus 51 squared plus 44 squared plus 50 squared plus 42 squared, etc. And that gives me this value in there. All right, so now I want to calculate the T for every treatment condition. I want to calculate the sum of squares for every treatment condition. And I want to calculate the P for every participant. So to get the T, what do I do? Yes, exactly. Add down this column, right? So 257 is the sum of all of these added together. 272, sum of all of these added together. 298 is the sum of all of these added together. I want to get each P. What do I do to get each P?
Just add each condition for each person together.
Yes. All right, Amber, what numbers am I adding up to get P of 150?
45, 50, and 55 to get 150.
Yes, perfect. Exactly. Yep. So for 150, I'm adding up those numbers. For 129, I'm adding up these numbers, etc. Awesome. And then for each one of my sum of squares, I'm getting the sum of squares for this column, right? So the sum of squares for my pre-data, the sum of squares for my 3-month data, and the sum of squares for my 6-month data. It's inherently demoralizing when you've been walking around for an hour and your Apple Watch tells you to stand up. All right. So to get your total sum of squares, again, we're taking the sum of x squared, which we calculated on that first slide, of 38,855. From that, we are subtracting our grand total.
Art, could you go over how you got the sum of x squared?
Yes. So the sum of x squared is I'm taking every one of these data points, right? It's the same data points here. I'm squaring 45. I'm adding that to the square of 42. I'm adding that to the square of 36. I'm adding that to the square of 39, 51, etc. And I'm doing that for all of them, right? I'm adding all of them squared together. That make sense?
Yeah. Thank you.
Mm-hmm. So I'm taking that sum of x squared. I'm subtracting that grand total, which was 827, which I'm now squaring. And I'm dividing by the number of observations, 18. And when I do all of that, I get 858.94. To get my within treatments sum of squares, I'm going to take each sum of squares that I calculated for each treatment condition and add them together. Right, so I'm adding the sum of squares of the pre, sum of squares of the 3-month, and the sum of squares of the 6-month all together. And when I do, I get 715.5. All right, because the sum of squares total is equal to the sum of squares within plus the sum of squares between, the sum of squares between is going to equal the sum of squares total minus the sum of squares within. Or I can just do it computationally. And I'm going to take every t value, I'm going to square it, I'm going to divide it by the number in that column, and I'm going to add that to the other t values. All right, so I'm taking this 257, I'm going to square it, I'm going to divide it by 6, right, because I've got 6 participants here. And then you're going to add that to 272 squared divided by 6, because I've got 6 participants here. And then I'm going to add that to 298, which I'm going to square and divide by 6 again. So again, that 257 squared divided by 6, 272 squared divided by 6, plus 298 squared divided by 6. And then I'm going to subtract again that g value, which I'm going to square and divide by the number of observations. And when I do all of that, I get a between treatments sum of squares of 143.44. I could do a little sanity check here. So I could say my sum of squares total was 858.94. So 858.94 minus the sum of squares within, 715.5. Come on now. And when I do that, I get, in fact, 143.44. 2 different avenues of approach there, giving the same answer. All right. So whereas that would have been sufficient on Monday, that's insufficient today. We need to remove those individual differences. So again, computationally, we're going to take the sum of every p squared divided by the number of conditions minus that same g squared divided by n. All right, so I'm taking that 150 for participant 1. I'm going to square that, and I'm going to divide it by 3, because I've got those 3 conditions. I'm going to take that 129. I'm going to square it. I'm going to divide it by 3, and then I'm going to add that to the 120, which I'm going to square, divided by 3, plus 114 squared divided by 3, plus 165 squared divided by 3, plus 149 squared divided by 3. All right, so that does all of that in there. And once I've added all of those together, I once again am going to subtract that g, that grand total, that 827 squared divided by 18. And I get a between subjects sum of squares of 658.28. Now, I want to get the sum of squares error. What do I do to get the sum of squares error? Yeah, sum of squares within minus the sum of squares between subjects. Sum of squares BS. So when I do that, I'm going to take my, where are we? 715.5. And I'm going to subtract this 658.28. And when I do, what do I get? 57.2. Cool. So that was nice and easy to get. Now I need to get my degrees of freedom. Degrees of freedom, again, this is going to be n minus 1 for that total. Big N is the number of observations. So in this case, 18 minus 1 gives us 17. The degrees of freedom within treatments is the number of observations minus the number, of conditions. So in this case, 18 minus 3 degrees of freedom between treatments, once again, is the number of conditions minus 1, or 3 minus 1 gives me 2. My degrees of freedom between subjects is the number of participants I have minus 1, right? You could, again, in theory, write this like that. So that's 6 minus 1. That gives me 5. And then to get that degree of freedom error, just like the sum of squares error, we're going to take the degrees of freedom within, and we're going to subtract the degrees of freedom between subjects. So to get that error, we take that 15 that we calculated here, and we're going to subtract that degrees of freedom between subjects that we calculated here, and that gives us degree of freedom error of 10. So now, if I were to plug all of this in, right? I have the between treatment, within treatment, between subjects, error, and total. You can once again see how everything relates to one another. Right? That error is just the within minus the between. Same for that sum of squares. The total is the between plus the within. To get your mean squares, you take your sum of squares and divide it by your degrees of freedom. And then somebody remind me, what is the F ratio for this repeated measures test? What do we put where? Well, so it is, there is a mean square in the top, and it is the error component, but which mean squares are you putting where? Yep, so it's mean squares between treatments over what?
Mean square of the error.
Yes, exactly. All right, so in this case, it's going to be 71.72 over 5.72 And that's going to give us this F value of 12.53. So I'm going to look it up in the back of my book, except I once again forgot it in my office. So when you're looking it up in the back of the book, it again is asking for the degrees of freedom numerator and the degrees of freedom denominator. Right? So in this case, what is the degrees of freedom numerator? It's Appendix B, but I don't remember what page. So it's the F table. So again, we're doing between treatments over error. So that degrees of freedom would be the same, right? So it's degrees of freedom between treatments over degrees of freedom error. So in this case, the numerator degrees of freedom would be 2. The error degrees of freedom would be 10. And you use that to look up your F critical value. Oh, thank you. I didn't mean to steal it from you. So I'm going to walk around the class and then I'll come show you all on Zoom here. So you see the numerator you've got up top here. So that's the 2 degrees of freedom. For the denominator we just calculated, it'd be the 10. You come over and find where they actually are. All right, so y'all can see, yeah, the numerator, we have 2 degrees of freedom here for the numerator that we just calculated, that between treatments. And for the denominator, 10 for that degrees of freedom error. We go over, we find it, that intersection there. You see you have 2 numbers. I assume you can see that we have 2 numbers. One is light face, one is bolded. The bolded one is at 0.01. The non-bolded one is at 0.05. Whichever one the test asked for. So if it's at the 0.05, you would evaluate against that. If it's at 0.01, you would evaluate against that. So does that make sense? So you have your degrees of freedom numerator. We have 2 there. For the degrees of freedom denominator, we would come down to 10. We would look at that intersection right in there. See the light face is the 0.05 value. The bold face is the 0.01 value. Does that make sense? Cool. All right. So, any questions about that?
Yes. Could you please go over the degrees of freedoms? Because they're getting mixed up in my head.
Sure, like how to get the degrees of freedom?
Yes.
Yeah. So the degrees of freedom total is just like we did before, where it's the total number of observations, or in this case, 18 minus 1. The degrees of freedom within is just like we did on Monday, so it's the number of observations minus the number of conditions. So 18 minus 3 is 15. For between treatments, it's just like we did on Monday, so it's the number of observations, k minus 1, or 3 minus 1, or 2. For the degrees of freedom between subjects is the number of subjects you have minus 1, or 5. And then that degree of freedom error is just the degrees of freedom within minus the degrees of freedom between subjects, right? And so then when we look at it here, that between treatments, degrees of freedom, again, is just k minus 1. That degrees of freedom total is n minus 1. The degrees of freedom within treatments is n minus k. And your between subjects is going to be p minus 1. And then your degrees of freedom error is just going to be your degrees of freedom within minus your degrees of freedom between subjects. Does that help?
Yeah, but it seems like you only used the 15 and the 5 to get 10, What was the point of getting the 2 and the total?
So the point of getting the 2 is you need that to get your mean squares value for your between treatments, right? So it's the sum of squares divided by 2 to get that mean squares. And then the total is a byproduct of knowing the between and within, right? And so if you've already calculated the within and you calculate the total, you can just get the between, or if you have the within and the between, you can just add them together to get that total.
Okay. Thank
Mm-hmm. All right. So again, if we wanted to be doing an effect size, we again are looking at the percentage of the variance that we can account for by treatment effects. So like we talked about last time, we're going to use eta squared. Just jump straight to it. So to get the eta squared value, we're going to take that sum of squares between treatments. All right, so that's sum of squares between treatments here. And divide it by the sum of squares error plus that sum of squares between treatments. So in this case, we're going to take that sum of squares between treatments, so 143.44. No, crap, come on. 143.44. We're going to divide it by 143.44 plus that sum of squares error, which is 57.23. Somebody quickly do that math for me. I'm not that good. All right, I'll do it. No, what's that? Perfect. 0.73. So that gives us our eta squared. That is a big eta squared. So that is a big effect. All right, questions about what we covered today? Yes, that is a big effect. Yeah, the standard is typically a 0.25 is a medium, and 0.5 is a large. The eta squared. So that's not the only, that's a good add-on, but I mean, the real answer here is you have this F value, which corresponds to the rejection of the null hypothesis in this case. What other questions do we have?
So does that F value make it retain or reject the null hypothesis?
I don't remember what the critical was, but if you look up in that table, so again, we had 2 degrees of freedom for the numerator, 10 for the denominator. Let's do it at the 0.05 level, so the non-boldface. 7.56 is that critical value. And so with an F value of 12.53, do we reject the null or fail to reject / retain? Well, so that's the question. So are we rejecting it or are we failing to reject it? Yes, rejecting it, exactly. Yes, because it is bigger. And now you could even look at the boldface one and say, okay, what is the boldface one? And that probably is going to be, well, it definitely will be a higher value, but we'll still probably reject a null for the 0.01, right? So you would say P is less than 0.01 rather than just P is less than 0.05. What other questions do we have? Is anybody feeling completely overwhelmed?
The only thing that overwhelms me is knowing I'm probably going to have to show my work on the test.
We'll figure out a good way of going about it.
The thing that's overwhelming me is that there's so many problems. I don't know how I'm going to keep it straight on a piece of paper.
Just like show the recording like
So for your exam, you will be able to now have two-sided cheat sheets. So yes, so you'll have more space to actually put all this stuff. All right. Well, I'll hang out if anybody has any other questions. Otherwise, have a lovely weekend. I'm sure you all spend your weekend doing statistics. So enjoy doing so, and I will see you all on Monday.